Anyone hungry? I have a handful of apples here. Since I've got 3, I'm in the mood to share. You want one? Here you go. 2 left. I worked up a pretty good appetite getting ready for this lecture. I'm not so sure that I don't want to eat both of these myself. What's that? You're really hungry. Well, all right, here. 1 left. What, you too? But this is my last one. You had better really need this. We've all been in a situation when we've had more than one valuable thing to give, just the way that I was a moment ago. Now, when you're flush with whatever that valuable thing may be, donating one of them is pretty easy. But I'm sure you noticed that as my inventory of apples became progressively depleted, I only released them grudgingly, each one more so than the next. And as I love to point out sometimes, molecules are a lot like people. The law of supply and demand still applies, even when it comes to protons. Let me explain. In our last 3 lectures, we've covered nearly 300 years of studying and understanding and applying acid-base chemistry. But we're not done yet. In the examples of acids that I've chosen so far, I've been careful to use Bronsted-Lowry acids that have just one acidic proton on them. Now, examples like our strong acid HCl and the weak acetic acid fall into this category. They have but one acidic hydrogen that can be released into solution. Sure, acetic acid has 3 more hydrogen atoms, but they're bonded very strongly to a carbon atom and cannot ionize in the way that the acidic proton can. We call acids like these monoprotic acids, meaning that only one proton can possibly be donated during the dissociation of these molecules. But all acids are not created equal. There are those that have more than one acidic proton. They have an inventory of multiple acidic protons to give up. And this lecture is dedicated to these types of acids and their more complex ionization processes. So now it's time to consider what happens when a molecule has more than one acidic proton. We call acids like these polyprotic acids. And here's a great example of one, phosphoric acid. Not a particularly large molecule, is it? Yet careful inspection reveals that phosphoric acid contains 3 hydrogens that could be fairly easily removed to create a conjugate base. Now, let's take a moment and consider how that will affect the behavior of phosphoric acid when it comes to acid dissociations. You might be tempted to conclude that 3 acidic protons in very similar chemical environments would simply all pop off at the same time, creating an equilibrium between phosphoric acid and phosphate ion, the complex anion containing 3 negative charges. But it isn't that simple. Deprotonation of weak acids like this one takes place in a stepwise fashion. And just like me and my apples, phosphoric acid gets stingier and stingier about donating protons as its reserve of protons gets depleted. It's easiest to put this into perspective if we compare a monoprotic acid with a polyprotic acid. Now, in the case of a monoprotic acid, something like, say, acetic acid, we have a situation in which there's only one acidic proton, so there's already sort of an intrinsic stinginess of giving that proton up. We've already figured that out mathematically. In this case, to deprotonate acetic acid, we have to get to the point where its Ka is finally sort of overwhelmed, right? But that's good enough for one proton, but when we have 3, we now have to consider the possibility that each one is a little bit different. The classic example is our polyprotic acid, phosphoric acid. Now, in the case of phosphoric acid, H3PO4, all 3 of these protons are in fact potentially acidic protons. So these 3 protons are a lot like my 3 apples from our example earlier. Which means that as my phosphoric acid begins to release protons, it's not going to let all 3 of them go at once. First, it will release 1 proton. In doing so, it's going to become dihydrogen phosphate ion and a proton. And there is an equilibrium that governs this particular deprotonation process. Now, sometimes you'll see these equilibria drawn with equal forward and reverse arrows. And that's all right, but to be really rigorous about this, I've drawn them in non-equal directions as an indication that this is a weak acid. But here's the catch. Dihydrogen phosphate itself still has 2 more potential protons to let go of. And when it lets go of a second proton, we have a second equilibrium. But this equilibrium, notice, is even less favored. The reason it's even less favored is I'm asking an already negatively charged dihydrogen phosphate to act like an acid and release another proton, gaining yet another unit of negative charge. So concentrating that negative charge on the conjugate base means that the conjugate acid in that step is weaker than the previous one. And sure enough, I've got one left down here, so my phosphoric acid can deprotonate yet again. When it does so, it gets 3 negative charges. Now it's a phosphate anion that has 3 minuses and, again, another proton. So you might imagine this equilibrium is even less favorable. And that's exactly the truth. Our final deprotonation is going to be behaving as though it were an even weaker acid than the previous. So what does this mean from a Ka perspective? Well, what this means is polyprotic acids get multiple Ka values. There's a Ka1 that governs the dissociation reaction in which phosphoric acid is the acid and dihydrogen phosphate is the conjugate base. There's a second equilibrium governed by a Ka2. In this case, dihydrogen phosphate is now the acid, and hydrogen phosphate anion is now the conjugate base. And, of course, there's a Ka3, which governs the final equilibrium in which hydrogen phosphate anion is our acid, and now phosphate anion is the conjugate base. And just as my equilibrium arrows here would lead you to believe, and of course the charges on the conjugate bases would lead you to believe, there's a trend in these values. Ka1 is always larger than Ka2, which is always larger than Ka3, because we're building up more and more negative charge as we release more and more protons into solution. In the case of phosphoric acid, which we'll be looking at quite a bit during the course, Ka1 is 6.9 times 10 to the minus 3. Ka2 is 6.2 times 10 to the minus 8th. That's 5 orders of magnitude difference in the equilibrium constant. And Ka3 is 10 to the minus 13th. Yet another 5 orders of magnitude difference. So you can understand now that there's a great difference in the relative acidities of these. And that is going to come into play when we start to try to predict the pH of solutions made from phosphoric acid and its other potential anion forms. So we can't just consider phosphoric acid in equilibrium with phosphate ion if we're going to model this polyprotic acid correctly. We have to include the other species that can form as a result of stepwise ionization. Specifically, dihydrogen phosphate and hydrogen phosphate must also be accounted for. Other familiar compounds, like the strong acid sulfuric acid, can do this. So can some familiar-sounding weak acids, like the carbonic acid that buffers your blood, the lactic acid that builds up in your muscles causing soreness after exercise, and tartaric acid, which is responsible for some of the tart flavors of grapes and wine. There are many examples of polyprotic acids. And to really be able to understand the sophisticated equilibria that drive the pH of chemical systems, we have to be able to understand and predict their behavior. So we've established that not all acids are created equal. Not only are there strong acids and weak acids which ionize to different extents, but now we have to include the fact that polyprotic acids can donate multiple protons to a solution. This leads us to an obvious question. Just how important are these second and third deprotonations when it comes to determining the pH of polyprotic acid solutions? Well, the good news is that most of the time they can be ignored for reasons we've already stated. If the Ka2 value is substantially lower than the Ka1 value, then it can be assumed that the second dissociation happens so rarely that it's not necessary to include it in an estimate of pH. Let me show you what I mean by that. Our goal in this case is to calculate the pH of a solution made by adding the neutral polyprotic acid to a solvent. Now, to do this, we're going to approach it very much like we did monoprotic acids. Here's our problem. What's the pH of a solution made by dissolving 49.0 grams of phosphoric acid in enough water to make a liter of solution? Well, in order to solve this, we're going to need a rice table, just like we did with our monoprotic acids. So we'll have to populate our table, remembering that the equilibrium we're dealing with here between HA, a proton, and A- in this case is a specific equilibrium. It's the one between phosphoric acid and dihydrogen phosphate acting as its conjugate base. So let's get started, as we did before, by calculating the initial concentration of the acid in our mixture here. Of course, we want that to be in molar. So I'll use 49 grams as my starting amount, 1 liter as my volume of solution. But to get to moles per liter, I'll need a unit that cancels grams and gives me moles. That is, dividing through by the molar mass of phosphoric acid, which I'm estimating at 98.0 grams per mole. Unit analysis tells me I'll be getting this calculation right. So, my initial concentration in this case is 0.500 molar. Well, let's put that where it belongs, up here in the initial concentration of phosphoric acid. Because I have not yet accounted for the ionization that's going to lead to my equilibrium, I'll use 0 for my proton and conjugate base concentrations. Now I can use the reaction stoichiometry to determine the changes, and those changes to determine a function for each of the equilibrium concentrations. Next, I need to worry about my equilibrium constant, and notice that I have chosen Ka1 as that mathematical constant that's going to govern my calculations. This is a crucial choice in this particular process. If we were to use Ka2 or Ka3, we would not get the correct answer. Now in this case, we know that the equilibrium concentrations of conjugate base and proton are just equal to x, so they become x squared. And of course, the equilibrium concentration of phosphoric acid is 0.500 minus x. I'm going to use my simplification, assuming that x is much smaller than 0.5. When I do that, the math is a little bit easier. I'll put Ka in there, 6.9 times 10 to the minus 3. Remember, Ka1, because I'm dealing with that first deprotonation equilibrium. This gives me an answer of 0.0587 molar protons. So this is my hydrogen ion concentration, assuming that it's much smaller than my phosphoric acid concentration. Now in this case, we're awfully close, aren't we? So although we can calculate a pH using this estimate and get 1.23, if we want to be thoroughly correct, we really don't want to use this assumption because we've exceeded a 10% threshold as far as the concentration of protons at equilibrium versus our initial concentration of phosphoric acid. So if instead we actually were to use the quadratic equation and not eliminate this x variable, we would instead calculate 0.0555 molar for our proton concentration, and our pH is in fact slightly different. It's 1.26 in this situation. Now, again, to keep things relatively simple, I'm going to go ahead with the estimate that it is smaller, although this is really pushing the limits of using that estimate. But when I do that, there's another question that comes to mind, and that is, if there are potentially second and third deprotonations, what are their contributions to the pH of a solution made in this way? What is the contribution of dihydrogen phosphate when it acts not as the conjugate base, but instead, right, that little bit of base that I made could instead act as an acid, right? Releasing yet another proton and forming a hydrogen phosphate anion as its conjugate base. Now to estimate this, I simply take the concentration that I determined in my previous equilibrium, because this number is also equal to the concentration of H2PO4, right, based on our first equilibrium. Which means I can use it to estimate that secondary equilibrium and how much proton it will create. Doing the exact same approach as I did before, having none to begin with, and then determining my changes, determining my final concentrations, I now have a situation where I can use Ka2, right? And in this case, Ka2 returns to me an answer of 6.03 times 10 to the minus 5 molar. In other words, far less. So we got lucky with polyprotic acids and their effect on the pH of solutions. Most of the time, we can ignore the minor contribution of second and third deprotonations. But our luck's about to run out as we consider how polyprotic acids behave in other familiar experiments and preparations. Consider adding a base to a polyprotic acid, like oxalic acid. Oxalic acid has two acidic protons. And it may look small, but its effects on global health are inescapably huge. When fully deprotonated, this diprotic acid becomes oxalate, a primary component of many types of kidney stones. But oxalates aren't all bad. The same anion that can make up kidney stones is also a critical component of the anti-cancer drug oxaliplatin, a compound that wreaks havoc on the DNA of rapidly growing cancer cells, slowing tumor progression in critically ill patients. So whether you're a urologist trying to prevent oxalate from accumulating in your patient's kidneys or an oncologist using it as a life-saving medicine to kill cancer, you can see why the protonation state of this little acid molecule can be critical to the equation. Now this time, instead of just adding a neutral polyprotic acid to solution and observing, we're going to force its hand, removing those protons by the addition of another reagent. This time let's look at oxalic acid. Now, oxalic acid looks like this. It's a diprotic acid. It has two acidic hydrogens that can be removed. So let's consider what happens first when we make a solution of this neutral oxalic acid. Now the first equilibrium, the one that's going to dominate at that point, of course, is going to be the deprotonation of oxalic acid. We're going to use solid sodium hydroxide, and that's going to create hydrogen oxalate anion, the conjugate base of oxalic acid. So just as we did before with our monoprotic acids, let's progressively add more and more base and see how that affects the population of acid and conjugate base in solution and how that's going to drive the pH changes that occur as a result of adding that base. I'll get my plot going here and my initial and final numbers of moles. Now initially, let's start with 1 mole, and let's say we're in 1 liter to make the math simple. So this is 1 mole per liter oxalic acid. Having added no sodium hydroxide, that puts me down here on this diagram. Now I can calculate that pH using Ka1 of oxalic acid. As I add a small amount of base, I change a small amount of that oxalic acid into hydrogen oxalate. And so I have to go to Henderson-Hasselbalch, but I can calculate the pH of that solution as well. And again, as I progress through this addition, let's say we go to half an equivalent. That reaches our halfway point, right? And we continue on through to the equivalence point for oxalic acid. We get a plot that looks something like this. So at this point, we have to consider the fact that we're getting up now to where we've got a nice, healthy amount of hydrogen oxalate, but we've completely depleted the oxalic acid. Now with a monoprotic acid, our titration would be done. But this is not a monoprotic acid. It's a diprotic acid. And the addition of even more of this sodium hydroxide is going to continue to shift the equilibrium, but now it's going to shift the second equilibrium in which hydrogen oxalate anion is the conjugate acid, and oxalate anion itself is the conjugate base. So let's set that chart up and continue adding incremental amounts of sodium hydroxide beyond this equivalence point for part 1. We very quickly reach a point where we have to start using Henderson-Hasselbalch again to determine the amount of each of the two in solution. But remember, this time it's going to be governed by the pKa of hydrogen oxalate, not oxalic acid itself. As we progress through, we get another kind of sweeping in the curve there, and we finish off right about here. So notice that I have 2 transitions now in my diagram instead of just 1. As I continue adding base, I first sweep through one area where I have a leveling off. That corresponds to the point where oxalic acid and hydrogen oxalate are buffering. So that will be right about the pKa of the first deprotonation, or 1.2. The second little distortion in my curve here is going to be where the second equilibrium is running the show here. So at this point, we're dealing with a situation where the change is happening at a pH of 4.2, which is roughly the pKa of hydrogen oxalate when it acts as an acid. So this is the equilibrium that's in charge during that second distortion in my titration curve. So in the case of oxalic acid, we have to be careful to consider the fact that there are going to be multiple equilibria that are going to change the shape of my pH curve in response to the addition of base. So that second Ka value isn't negligible this time. It turns out to be critical in determining the conditions under which oxalic acid will become oxalate, with all of the health benefits and perils that come along with it. Now, when it comes to using polyprotic acids in buffers, these multiple ionization equilibria also have to be carefully considered. The use of polyprotic acids in buffers is not without its complications, but also not without its benefits. We've actually already seen a polyprotic acid used as a buffer. The buffer in your blood, carbonic acid, is used to prevent your blood pH from dropping too far below its optimum value of about 7.3. Now we know there are two equilibria, but it's actually the buffering equilibrium between carbonic acid and bicarbonate that, at least in part, moderates your blood pH. Our previous example of hyperventilation relied on the fact that dissolved CO2 creates a certain amount of carbonic acid in equilibrium with bicarbonate. Our new understanding of buffers and the polyprotic acid carbonic acid finally allows us to take a closer look at the hyperventilation fit that I tried to give you in our previous lecture. Now, we usually think of carbon dioxide as a bad thing. It's a waste product of respiration that we exhale to get rid of. But in truth, your body needs a certain amount of carbon dioxide to maintain proper blood chemistry. Exhaling too much carbon dioxide, as happens during hyperventilation, causes an imbalance in the dissolved carbonic acid in your blood. Think of it in terms of Le Chatelier's principle. As you hyperventilate and expel more carbon dioxide from your lungs than you normally would, what will the blood coursing through those lungs do in response? Of course, it will respond to the stress by trying to replace that carbon dioxide that was removed from the natural equilibrium. But that means that the carbon dioxide has to come from somewhere, and it comes from your bloodstream. Now, another way of thinking about this is in terms of Henry's law, which tells us that lowering the partial pressure of carbon dioxide in your lungs should lower its solubility in the blood within them. Now, this causes dissolved carbon dioxide to escape. As the carbonic acid in your bloodstream decomposes to create that carbon dioxide, the pH regulating effects of the carbonic acid bicarbonate equilibrium in your bloodstream are lost. With less carbonic acid, your blood pH begins to rise. Now, other buffering systems will try to kick in, but if the change is too rapid or too drastic, they can be overwhelmed. And the rise of blood pH is commonly called respiratory alkalosis. It can cause a host of problems, not the least of which is that hemoglobin, a complex biomolecule that shuttles oxygen to your cells, starts to have trouble releasing its molecular oxygen passengers at their destination. So in an odd chemical twist, this means that breathing too rapidly or heavily can actually cause your body to starve of oxygen. This causes the classic symptoms of dizziness, tingling, and confusion that we've come to associate with hyperventilation. It also explains why the classic remedy of breathing into a paper bag is sometimes recommended. This traps the CO2 that you exhale and causes you to re-inhale a greater concentration of CO2. Both Henry's law and Le Chatelier's principle predict that this remedy should help because it encourages more carbon dioxide to dissolve into the bloodstream and rehydrate to become carbonic acid again. At least it should help temporarily while you calm yourself down to the point that your body can get things back to normal. Carbonate buffers are hardly the only biologically relevant buffer system. There's one other polyprotic acid system that I'd like to discuss in this lecture, and that is phosphate buffers. Phosphate buffers are remarkably versatile tools in both your body and in the chemistry lab. Cells use them to maintain the pH of the solutions inside of them, and researchers use them to establish a variety of controlled pH conditions to allow them to make observations in well-regulated pH conditions. So, what makes phosphates so special? Well, the answer to that question begins with their triprotic nature. Phosphoric acid, dihydrogen phosphate, hydrogen phosphate, and phosphate itself all coexist in equilibrium with one another in aqueous solutions. If we give phosphoric acid the same treatment that we did oxalic acid and try to determine how its proportions of all of the various species that it can create varies with pH, what we notice is that it's really quite complex. Let's start down here where we've added very little or no base at all. Now, initially, there is a little bit of a buffering zone here, and that is right at the pKa of the first dissociation of phosphoric acid, right around 2.16. As we continue, right, we pass through a point where the equilibrium in between phosphoric acid and dihydrogen phosphate has now been overwhelmed, and we're dealing instead with an equilibrium between dihydrogen phosphate and hydrogen phosphate acting as acid and base respectively. This occurs right around 7.12 pH. That is equal to the pKa of dihydrogen phosphate. And sure enough, there's a third region of this plot in which we see yet another leveling off, that occurring near the pKa for the third ionization, which would be the equilibrium between hydrogen phosphate anion and phosphate anion. So as you can see here, phosphate offers a really great buffer system here, not just at one pH, but over a range of multiple pHs because it's a polyprotic acid. And simply by adjusting conditions, we can determine which of these three equilibria are in charge of the pH of the solution. So it should come as no surprise that pH buffers meant to emulate physiological bloodstreams nearly always are phosphate buffers. Because of the pKa of dihydrogen phosphate ion, solutions of these buffers were used by Søren Sørensen to investigate the effects of pH on proteins found in living systems. And they did a remarkable job of this. But these buffer solutions gave him a way to conduct his investigations without any living host to complicate the process. What makes phosphates and other polyprotic acid buffers particularly versatile is the fact that buffer solutions can be created at various pH values. So let's summarize this lecture's material. We started thinking about what can happen when acids have not just one, but many acidic hydrogens. We thought about how multiple protons are released in a stepwise process, which creates a more complex equilibrium among multiple conjugate acids and bases, each being less acidic than the previous. We realized that this meant we were able to get away with neglecting the effect of second and third deprotonations most of the time when a polyprotic acid solution is formed simply by adding the acid itself to water. But as our discussion progressed, it became evident that these species can't always be ignored. We saw how the neutralization of polyprotic acids creates a pH curve with a more complex set of features than we've seen previously. Specifically, we see multiple inflections in the pH curve as each subsequent equilibrium is established, then overwhelmed by the addition of more base. And finally, we took some time to think about how these polyprotic acids can be used in buffer solutions. We saw that not only can they be used as buffers, but that the range of useful pHs is expanded because we now have a choice of which conjugate acid-base pair is going to be doing the buffering. Although they will appear from time to time as we move on to new topics in the course, our focused tour of acids and bases is almost at an end. In the past few lectures, we've discussed the pH scale, strong and weak acids, polyprotic acids, and many aspects of their behavior. But now it's time to come full circle and ask a more fundamental question. We have seen the critical role that the Ka values for acids and Kb values for bases can play in the chemistry of these useful compounds. But before we move on, we need to ask ourselves why Ka and Kb values span such a huge range of values. What really makes one acid weaker or stronger than another? We're going to try to answer those questions by tying molecular structure to acid-base properties in our next lecture.